we need to understand the anatomy of a micelle and how the anatomy of micelle is important to understand in terms of the bioapplicability. Now I'm going to connect the fundamentals to the applied part of this lecture series. Before going, so again, just reminding you that we have tried to understand the characteristic properties of the amphiphilic molecule. Those are surface active, surfactant, their aggregation behavior. Now we will go ahead with the quantification. Quantification of the bulk and the interfacial properties. Quantification means how we can measure different characteristic properties of the aggregated phase. Among them, the first one is the stability of the micelles. Remember, we talked about the stability of the nanoparticle in yesterday's lecture. So this time we are going to talk about the stability of the micelle. You have to keep in mind that stable micelles are the most important entities to produce the stable colloidal solution. So we have to have the stable surfactant structure which produce stable micelles. So I'll explain what is the meaning of the stability here. But how we can determine the stability? So stability we determined in terms of free energy. You all know what is the definition of the free energy and how we can evaluate the free energy of the micelle formation. We begin with the chemical potential. Chemical potential of the surface active molecule in the micellar state, that is mu. Under standard state condition, that is a naught as superscript. M stands for the micelle as subscript. The chemical potential of the surfactant in the micelle is equal to the chemical potential in the monomeric form. This one stands for one molecule. Monomeric form in the standard state plus RT, gas constant, absolute temperature multiplied by ln, natural law, activity. You know that what is the meaning of the activity. Activity is related to the activity coefficient and concentration. If you go through the physical chemistry and there in thermodynamics, you will be able to understand what is the definition of activity. So here we are talking about the activity of the surfactant molecule or the surface active molecule. If I rearrange this equation, take this mu1 on the right hand side, so the difference in the chemical potential in the micellar state to that of the monomeric state and the micellar state, I mean to say that which states we are talking about. So I'm saying that this is the monomeric state of the micelle where you have only the surfactants in the monomeric form, and these are the micelles. Okay, so you have the chemical potential is standard state 1. You have the chemical potential of the surface active in mu. This is mu in the micellar state. So the chemical potential in the micellar state minus that in the monomeric state, that is the standard free energy of the micelle formation. So it is the difference between the chemical potential between the monomeric and the micellar state. That is the definition of the standard state free energy change for the micelle formation. You know the definition of the free energy. So the spontaneous process should possess negative delta G and or the zero. If the spontaneity or the delta G value is 0 or negative, it means that the process is spontaneous. We will try to understand that in what circumstances the micelle formation is a spontaneous process. So therefore we are expecting to achieve delta G negative. So delta G micelle formation standard state RT ln X. Here the activity is replaced with the mole fraction of the surfactant in the micellar state. So in the micellar state, the mole fraction of the surfactant is equated with the CMC, critical micellar concentration, CMC divided by 55.5 moles of water, right? So you can simply substitute that value of X with the X CMC and further rearrange it. And now it is delta G micelle formation, that is RT ln X CMC. What is the meaning for this? I mean to say that if you substitute this value, you take the CMC, divide this by 55.5. CMC you can determine from the conductivity or the surface tension. Divide this by 55.5, take the natural log, multiplied by the temperature at which the experiment has been performed in Kelvin, multiplied by the gas constant, and you will have the delta G of the micelle formation. You can directly calculate the value. Under what circumstances this value could be negative? Actually, the standard state micelle formation is the contribution from the hydrophobic component and the polar component. So it means that what is the meaning for this? The meaning for this is that the contribution for the delta G formation is originating from the contribution of delta G of the hydrophobic. HB represents the non-polar part and delta G S is the polar part. If I add these two, so I have delta G of micelle formation. So therefore I can split the micelle formation free energy into the contribution of hydrophobic free energy contribution and the hydrophilic free energy contribution. You could see here I have defined due to the hydrophobic interaction and due to the electrostatic interaction. When the micelle is formed, uh, the hydrophobic interactions are here. So this is the hydrophobic interactions between head group and head group. So it is delta G HP. And these interactions between polar and polar, that is delta G, the polar interaction. You know that in order to create a micelle, a aggregate, I need to minimize the repulsion between positive and the positive charge, and I should enhance the attraction between non-polar and non-polar. So if you look at the structure of the micelle like this, if I have to place another one over here, and the longer the non-polar part, the stronger are the interaction. Stronger are the attractive interaction, right? And if the polarity is enhanced over here, the greater are the repulsions, right? So I have to minimize the repulsions to have the compact arrangement, and I have to enhance the active interaction that leads to the stable micelle formation, right? How do I know that? In what way I can? There are ways to create the stability. If I increase the length of the hydrocarbon, the van der Waal interactions, non-polar interaction will enhance, and in this way, the micelle is going to be stabilized. If I reduce the polarity, thereby I am reducing the repulsive interactions, and hence the head group will be lying closer to one another, and this way the micelle is going to be stabilized. So, what is the spontaneous process? Now it is the contribution of these two. In order to make the delta G negative, you see the negative sign over here, I need to increase the attractive interaction of the hydrophobic contribution. So increasing the hydrophobic contribution will make the change spontaneous. So this is a negative contribution of the hydrophobic, I mean to say that it enhances the spontaneity. So that is referring to the negative sign, right? On the contrary, the delta G becomes positive when there are stronger repulsive interaction between the head group. So these head groups, those are being provided by the delta G S, that is the hydrophilic contribution, right? So in order to achieve the negative free energy of micelle formation, hydrophobic contribution in comparison to that of the hydrophilic contribution. Hydrophilic contribution is contrary to the micelle stability, so its delta G formation is positive. Hydrophobic contribution is is enhancing the stability, so therefore its contribution is negative. So you have to enhance the negative contribution in comparison to the repulsive contribution contributed by the polar head group. So those factors which will enhance the non-polar interaction and reduce the repulsive interaction will automatically make the delta geomycin formation negative and the process will be spontaneous. That is the meaning of this whole story. So suppose if you ask me when the micelle formation take place, so here when the micelle formation takes place from the monomeric to the micelle, it is spontaneous, so the delta G is always negative, right? If the delta G is positive, there will not be any micelle formation. In other words, I'm going to say that if there are strong repulsive interaction, we cannot place the molecule in a kind of an aggregate. So the resulting delta G will become positive. So therefore, we have to reduce this repulsive interaction to have the micelle formation, and those surface active molecules which produce micelle, they have always the hydrophobic contribution is much more enhanced in comparison to the hydrophilic contribution. So that is the meaning of this whole story. Suppose if you ask me, if you are not working in this project or in this kind of a project or a direction, you may think it is completely a theoretical, but there are ways to calculate delta G. I mean to say that if you measure the CMC, as I've told you in the previous lecture, that you can measure it from the conductivity or from the surface tension by first measuring the CMC, and then you are substituting the value over here, calculating delta G, and then you can split the delta G into different contribution. So there are ways to calculate quantitatively the hydrophobic and hydrophilic contribution. Uh, Another quantitative is slightly more intensive mathematical expression. So we are picking the same equation, the one I'm saying over here. It's the same equation where we have picked over here, right? And what we have done, so the delta G micelle formation contribution is coming from the terminal methyl group. So here is the terminal methyl group of the hydrocarbon chain plus M or the N number of methylene group, and there are, if there are 12, so you have one terminal, 11 are left, so it means that the value of M is 11. The contribution of each of the methylene group is delta Gm multiplied by M plus the contribution of the delta G from the head group region. This W stand for the head group region, right? And all these contributions, and from the solubility of alkanes, we can have the contribution of the terminal methyl group. We can convert into the methylene group, and we can substitute this, and the entire formulation is now in the methylene group. So we have two parts now. The equation, this top equation now have taken the form of this because I've substituted the value of delta G in this equation and rearrange it in this form. So suppose if you ask me how we have done it, you can easily do it at home. You simply rearrange the equation. First you you see the log. Uh, so first what you can do, here it is ln. The first thing you will be doing, you are converting ln into log. You know how you can do it, right? And then eventually you are going to get equation. And then the delta Gm contribution is given by this entire terminal and methylene groups and the head group region. You are going to substitute the value of this delta G terminal from here in this equation, and this equation then you are going to insert it over here, and this is the resulting equation. You can do it by yourself. There is no difficult mathematics involved in this case. You are going to split this portion into two parts. This part of the equation up to here is, you can label it A, other one is B. I'm going to explain what is the meaning of this, multiplied by the value of N. So N is the same which we talked about in the previous lecture, aggregation number. If you have the CMC, log of CMC, if you are going to plot the CMC from different surfactants with different value of N, obviously if you are going to choose different surfactants, all the aggregates having the different value of the N, that is the aggregation number. So all different surfactants having the different CMC, if you are going to plot the log CMC against N, this is the slope part, slope is B. This is the intercept, intercept is A, right? So you can calculate the value of A and B from the intercept and from the slope. And now how it is going to help us? The A value, from the A value, you can substitute the gas constant, temperature, take the log of 55.5. Eventually you will be able to calculate the head group contribution. This is the head group contribution. By equating the entire term with A, you can calculate the delta G for the head group contribution. By equating the entire term, the second term with B, B you have already calculated from the slope, you can calculate the delta G of methylene contribution. So I mean to say, this is the way we can have these two contributions, right? If you want to have the contribution, hydrophobic contribution, the hydrophilic contribution, this is the way you can do it. So I mean to say that this is, in fact, it's a slightly intense theoretical characteristic properties to calculate to evaluate for the CMC of the different surfactant. Probably you may not need it, but I just wanted to tell you that this is the way we can quantify. Okay, so apart from the delta G, we have other thermodynamic parameter. So you can calculate delta S as well, right? And when delta H, that is enthalpy, is constant over a temperature range, so you can calculate the entropy of the micelle formation. You can also calculate the enthalpy of the micelle formation. You have calculated delta G. From the delta G, you can calculate the delta S, entropy of the micelle formation, and the enthalpy of micelle formation. So this is all about the quantification in physical chemistry or in thermodynamics term, right? So I just wanted to let you know that this is one way of determining that how much micelle is stable, delta G. Now we are coming back to our previous story. Remember I told you the anatomy of the micelle, and I told you the different parts, and I told you that the micelle is in fact a single pot, and this single pot has the ability to dissolve all kinds of molecules. All kinds of molecules range from the non-polar to all the way to the polar. How we can do it? So this part is entirely polar. The polar part is slowly converting into the non-polar part as you move from the surface to the center. It means that this is entirely polar, predominantly polar, less predominantly polar, and entirely non-polar. Okay, if that is the story, so how can we solubilization in the micellar phase? How can we pick the sites for the solubilization of the different species? So I'm going to explain what's the meaning for that. Uh, just a minute. So you already know that what is hydrophobicity? That is the hydrocarbon chain length. We can increase the hydrophobicity, non-polarity of the micelle by increasing the chain length from here to here. Hydrophilicity can be increased by having the stronger polarity. This one in comparison to this one. Branching, unsaturation or the saturation. Here you could, because here I've shown you only the normal hydrocarbon chain. So you can have the, here it is completely saturated. There is no, the hydrocarbon one chain with the unsaturation, that is the double bond. But keep in mind, by adding the unsaturation, so the hydrophobicity, the non-polar ability of the bicycle that reduces, because the unsaturation is some degree of polarity that you are going to introduce. So therefore, means suppose if you want to have entirely a non-polar micellar core, it means that you have to avoid the unsaturation. So head group modification, you see here, this is sodium dodecysulfate, SO4 oxygen. Here it is triphenyl phosphanium, this phenyl. This one is butyl, this one is methyl, and this way. So I mean to say that you can change the head group modification, and obviously when you have the oxygen, so the polarity is going to be affected. When the negative charge is on the terminal functional group connected to the central atom, and in comparison to when the charge is on the central atom of the head group, so there's a difference in the intensity of the charge. So that also changes the ability with which the charged portion is going to interact with the other charged portion. Suppose if you have to solubilize the ionic compound in a micelle, ionic compound or any polar component, or any polar solute you solubilize in the micelle, that will be solubilized in the stern layer. Stern layer is polar, so the polar portion is going to be absorbed in the stern layer, right? So here AB represents the salt. The negatively charged ions are going to be adsorbed on the interface that enhances the stability or the solubility of the electrolyte. So electrolytes can be solubilized in the microphase solution. Polar covalent compound, alcohol, ethers, and esters can be solubilized. They are not entirely polar. Like I suppose if I say the propanol, butanol, pentanol, or hexanol, they are not entirely polar, right? How they are going to be solubilized? Suppose if someone asks you, I understand that this is the micelle, right? But the question is, if this is the micelle, and if I am dealing with the alcohol, OH, right? Pentanol, you can say C5. I can represent it just like that of a surfactant molecule. How it is going to be solubilized? I'll be saying that this is OH now. So OH will be over here. OH has to be here because this is the polar region. This is the polar region. OH is going to interact electrostatically. OH is having the dipole, so it is going to interact with the positively charged head group, whereas the CH5 is a shorter tail in comparison to C12. It will be closer to the non-polar region. So therefore, this is the way the solubilization is occurring for all of them. Alcohols, higher alcohols, ethers, and esters. The polar functional groups of these molecules will be closer to the stern layer. The non-polar will be closer to the non-polar part. If you are dealing with entirely hydrocarbons, hydrocarbons are completely non-polar. The solubilization of the non-polar is going to be in the core. The core is entirely non-polar, so therefore the hydrocarbons are going to be solubilized in the non-polar region. What if we are dealing with the solubilization of the polymer? So here we have different kinds of polymer, neutral polymer, polyelectrolytes. Like here you can say that if we have the polymer, right, and in the polymer you have the side chain, so then the polymer is going to wrap the micelle. It is going to wrap the micelle like this. The polymer without the side chain is again going to wrap it like this. So it means that it's not just one micelle that is going to associate with the polymer. Number of micelles are going to associate with the polymeric molecule. Now, if the polymer is having longer hydrophobic functional group, so this is the longer hydrophobic portion of the functional group of the polymer molecule. So it will try to fold and enter into the palisade layer, right, in order to entrap the micelle. What if we are dealing with a polyelectrolyte? This is the anionic polyelectrolyte. Anionic functions are repeating in the polymer backbone. This is cationic polyelectrolyte. The positive charge is repeating on the polymeric backbone, right? And then, depending upon the charge on the micelle, they are going to be absorbed at that portion. If the micelle is negatively charged, it is going to take this position, as you could see over here. And there are two ways then, because the micelle is positively charged, so the monomers are also positively charged, right? So then the monomers are first going to interact with that of the active sites, oppositely charged sites. You see the monomers are attracting, you see the micelles are attracting. So suppose if you ask me, what could be the conductivity behavior in that case when we are dealing with the polyelectrolyte, or we're dealing with the ionic or the cationic surfactant? So as we start adding the surfactant, cationic or anionic surfactant in the polymer solution, the conductivity increases slowly, and you will see the first break. The first break belongs to this kind of aggregation where monomers are going to interact with the active sites. We call it critical aggregation concentration. It is not the critical micelle formation. When these positions are occupied by the monomeric molecule, we are still increasing the concentration of the surfactant. Eventually, they will take the turn into the micelle because you have to accommodate more surfactant. So therefore, the monomers will aggregate at the same pocket positions in the form of the aggregate, and you have now CMC over here. So the actual CMC of the surfactant in the presence of polymer is over here. The first break is the critical aggregation concentration. So you can show it like this. The critical aggregation concentration, it obviously when you have just the monomeric form associated with this, right? When the sites are occupied, if you keep on increasing the concentration, eventually these all sites are occupied by either the monomers or the micelles, and then you will see the free micelles of the surfactant. And so therefore CAC arrives before the CMC. CAC must be a must. You will see the CAC before the CMC. So CMC is only when all the active sites of the polymer are occupied, and then the added surfactants, so they are going to be in the aggregated states of the micelle. Now, what is the purpose of this information? The purpose of this information is that I'm taking you to slowly to the bioapplicability. The purpose of this information is because there are plenty of products in the cosmetic industry or in other pharmaceutical industry where you have the micellar systems in action. How? I'm going to explain that. First, I'm going to take the most common examples, the applicability of the surfactants. We talk about the the cleaning action in the previous lecture, that how the soap particles are removed or the clothes can be cleaned. In terms of the free energy, you need to make the dissolution of the oily particle spontaneous. It means this process must be spontaneous. Spontaneous process means this delta G should be 0 or negative. Where are the interfacial tension existing? This is the interface between gamma represent the Greek letter for the interfacial property, uh, uh, interfacial tension between oil and water. So you have a oil and water. So exactly at the surface tension that exists, that is gamma W. Oil and solid. So the surface tension that exists, interfacial tension exists over here, that is the solid and the oil. Surface and water. The solid surface and water interfacial tension exists over here, that the gamma, solid and water interfacial tension. How to make this spontaneous? So it means that delta G of the cleaning action when your washing machine runs, there are three contributions. The one is the interfacial tension between water and oil, solid and water, and solid and oil. This term is negative, the other two are the positive. So in order to make delta G 0 or negative, you have to have this term predominantly higher than the summation of these two terms, right? So now you see that what are these terms? So solid oil, the solid oil over the binding force, which is keeping the sticking the oil particle to that of your cloth or any surface. So this has to be removed, right? So this you are going to remove only when you are going to enhance the surface activity by putting the surfactant. So the surface activity here you cannot simply means there is no way you can merge the or you can I'll say introduce the surfactant molecules over here. There is no place, but you can reduce the surface tension of these two components by adding the surfactant. The surface tension of oil water is reduced. The surface tension of solid water is reduced by putting the surfactant. Thereby, the magnitude of the solid oil is automatically going to be increased. And thereby, we are going to have the delta G negative or 0, and hence the process is going to be spontaneous. This is the cleaning action. This is the most prominent example of surface active molecule and surfactant. Where are the biological applications? We are now going ahead with the biological applications. So the first one is the cosmetic cleaning. So you every day you use the lotions, right? And here is your outermost, right? And you have mainly the dead cells we call the horny layer, right? What you do in order to reduce the amount of the dead cells, you have the coating of emulsion. Usually the lotion is an emulsion. It is made up of the combination of oil and water. Oil and water you cannot mix. Then how you created the emulsion? Without adding the surfactant, you cannot create the emulsion. The surface active molecule is going to create the or going to help the mixing of the oil and water. So what that emulsion which you have or the lotions you have, you are going to coat it like this. This will act as a layer that will reduce the evaporation of water, keep the moisturing of the skin. This is another most important property of the surface active molecule. So what is emulsion? Emulsion is exactly the combination of oil and water, which your lotion is made up of. Oil, this black ball is representing oil, and the water is the blue shell, and the surfactant surface active molecule is binding these two faces, creating the lotion. And that lotion, when you are going to use, that is going to prevent the unnecessary evaporation from the skin, keeping it moist. Next one is entirely related to the human health. Human health, respiratory system. How the surface active molecules help us achieve that. Your lungs, in fact, they are working only because of the presence of lung surfactant. Them the lung surfactant. They are lining the alveoli. So you have alveoli. So you have the lining over here. That lining is created by the biological surfactant. So it is not those conventional surfactant which you are using in your laundry or in the soaping in your washing machine. These are the surfactant produced by the human body by itself, and we call them the biological surfactant, the lung surfactant. And they line all the alveoli internal lining. This is the air exchange. Air exchange is taking place. So these particles, you see that, so they are the air particles. So that exchange is taking place on the surface of the alveoli, right? You know that we are talking and we are breathing and without even sensing that we breathe. The reason is that because it is an automatic process. The nature has provided us the automatic process. Lung contracts and expands. Now, lung itself is a human flesh, and most of that part is in aqueous environment. So therefore, what kind of this interface is? This interface is predominantly aqueous phase and air phase, because the human body is predominantly made up of aqueous phase. So suppose if somebody asks you that since the surface active molecules are lining the alveoli, then they have to be at the interface. And which interface we are talking about? You will be saying that it is the interface between the aqueous phase and the air phase, not the solid phase. In the human body, except the bone, there is no solid phase at all, right? Okay. Now, what is the participation of the surfactant here? Uh, so we started. Uh, I think I have to finish it. 11. No, 12. 12, 15. Okay, I have to 20 minutes. Sorry. Yeah. Okay. So uh, the film of the surfactant, biological surfactant that lines the alveolus, that is very, very important. So anybody who's having the lung problem, that could be because of the pollution or any other reason. So this film is not continuous. This film is not continuous. I have also the same problem, and because after the vaccination, I have to keep the inhaler because the vaccination. So somehow my that biological surfactant concentration film, its concentration changed. I don't know what is the reason. Many of the people in North America, in Canada and USA, having the same problem. So slowly, the effect is going to diminish after 3 years, and I am feeling much more now better. Earlier, I had a very severe problem. Means it was not possible for me to even continuously talk for 1 hour. So I had to stop in between to drink water and then to speak. But now the situation has improved quite a lot, and I am continuing taking the lecture 1 hour, and there is no issue. So I mean to say that if you have a problem related to respiration, it means that something is wrong with the biological surfactant lining, right? And you could say acute respiratory distress syndrome in biology or medical term. So these terms are related to the fact that something is wrong with the layer of the biological surfactant that lines your lung. So it could lead to very serious consequences that if it is sometime if it is too severe, now obviously to lead to the fatal circumstances, because it is obviously the respiratory system, and if your respiratory system is going to collapse, no one will affect you, right? So now micro in high resolution, what is happening? So this is the high resolution image, right? Is a schematic region. Suppose if somebody asks you from where this, you see, it is the bilayer, exactly the bilayer which I was talking over here. The bilayer means, as I told you, that on the surface of the nanoparticle, this is nanoparticle, and this is the surfactant. Another surfactant is going to arrange like this. This is the bilayer, right? So the same bilayer, this bilayer, this is the bilayer over here. This bilayer runs on everybody's alveolus. Every alveolus in lung is lined with the bilayer. Okay, how this bilayer is produced? What nature has provided us? These are the bilayer is produced by you see these small vesicles. The vesicles are produced by type 2 epithelial cells here in the cell. These vesicles are released. You see they are released from the cell. They go at the interface and convert into bilayer. We talk about the micelle shape transformation. So we talk about the spherical micelle change to rod-shaped micelle, rod-shaped micelle change to bilayer, bilayer then convert into the vesicle. If you trace the process in the backward direction, that is happening over here. So you have the vesicles, vesicle unfold, break down, and they form the bilayer at the interface. So it means that this is air fluid interface. Air fluid, here it is the aqueous phase, and here you have the air exchange take place because it's empty, alveolus is empty, there is air inside, so that is the interface over here. For a normal person, this is a continuous bilayer. For those people who don't have any problem with the respiration, they have continuous bilayer. And I'm talking to you, you putting the attention without knowing that your respiration is working. Your lung is contracting and expanding because you don't have who has the respiratory problem, pressure on the lung to expel the air, to bring the air inside. So what happens when there is a problem? We call it injured lung for any reason. It could happen because of the pollution, right? So suppose if you imagine the pollutants are coming over here, or the way in most of the cases we have in North America now, this COVID vaccine side effect, and that what is affecting? It means that the COVID vaccine effect is somehow affecting this vesicle formation. If there is no sufficient amount of the vesicle formation, it means that there is a problem. This is not a continuous one. You see the broken bilayer? This broken bilayer cannot provide the sufficient amount of surface activity. If there is not a sufficient amount of surface activity, the contraction is not complete. The lung cannot completely contract to expel all the amount of the air. So there's a partial contraction. The partial contraction is the problem for the respiration. Okay, so just a minute. Yeah, okay, just a minute. What are the other slides? Yes. Okay, so now somebody can ask you that what is the composition of this surfactant? Which surfactant we are talking about? I have explained the chemical structure of the different surfactants. Ammonium salts, phosphonium salts, you have seen the ether derivatized surfactant, and so many more. But what kind of these biological surfactants are? You have to keep in your mind the biological surfactants are the schematically the structure is the same. They also have the hydrocarbon chain as well as the head group, but chemically functional group is creating the head group, polar head group for the biological surfactant, and which one for the hydrocarbon chain. And then we have here. These are the biological surfactant. Phospholipids are the biological surfactants. Among them, we have the combination of 70 to 30%, 70% DPPC, 1,2-dipalmitoyl SN-glycerol 3-phosphocholine. This is 70% composition, and POPG. So here are the name for different POPG, DMPG. POPG means it is C16 to C18 combination, and DMPG it is C14, and DPPG is C16. So all these are some of the sodium salt, or they may or may not be the sodium salt, but the sodium salts are highly water soluble, so we can solubilize them. So usually they are in the zwitterionic state. So you see over here. So this one is cationic, right? And no, zwitterionic, cationic. You see the positive charge and the negative charge. This one is in the salt formation. You have the sodium salt over here. So these are the polymerase surfactant. We call the polymerase surfactant. So the 90% of the phospholipids are the combination of DPPC and POPG. But plus then you have the 10% 100% of the surfactant proteins. Which surfactant proteins? You see the you are familiar with the proteins, but you see why I have used the word surfactant. How we can attach means how we can say the protein acts as a surfactant. If a protein molecule is surface active, protein is a polymer. It's made up of amino acids, you know already, right? But we call it a surfactant protein. So all proteins are surface active. You have to keep in mind. So albumin proteins, so they are not surface active, right? But some specific proteins which are being produced in the lung, so they are the surface active proteins. And you have three uh, for SPA, B, C, and D. These two, they are hydrophilic, predominantly hydrophilic surfactant proteins, and SPB and SPC, so they are the hydrophobic surfactant proteins. So I mean to say that, so I'm going to conclude it over here. This is the first bioapplicability we have talked about. This bioapplicability is, you have seen the difference. This bioapplicability without nano. But the main purpose is we are slowly arriving at the bioapplicability of the nanoparticle. But before arriving to that, because nanoparticles are coated with surfactant, you need to understand that how the surfactants are having the role played in the bioapplicability, and to understand the role of the surfactant in biological application, the best way to demonstrate that is the surface activity of the biological surfactant in your respiratory system. So finally, I must conclude the two lectures, because today's lecture were on the surface active molecules, their characteristic properties, their chemical structure, their non-polar and the polar functional group, and what kind of polar and non-polar functional group constitute surfactant molecules. There are different kinds of surfactant molecules: cationic, anionic, zwitterionic, and non-ionic surfactant molecules. And then we talk about their aggregation process. They are not conventional molecule. I mean to say that if you keep on increasing the concentration of sugar in water, you're not expecting to form the spherical particle like micelles. Sugar molecules are not going to arrange themselves in the spherical aggregate. The same is the story for sodium chloride. If you keep on increasing the concentration of sodium chloride in water, you are not going to have a specific aggregates the way you see the surface active molecule. Then what prompts, what drives the aggregation process in the specific spherical shape? It is the dual behavior, the dual functionality of the molecule. As long as the molecule is not possessing the two functional group, the one interacts simultaneously with the polar and the other one simultaneously with the non-polar, there is no way you can have a specific aggregates the way the surface active molecules produced in the aqueous phase. Sugar molecule, sugar molecule is not possessing predominantly hydrophobic phobic region. Sugar is highly water soluble, right? So because of its hydroxyl group and all other functional groups. And likewise, the sodium chloride is ionic, and practically there is negligible amount of the non-ionic character. So therefore, it's a highly ionic, it's a strong electrolyte, it will instantaneously solubilize in water, and there is no question of a specific aggregate formation at a particular concentration. But the specific aggregate formation at a particular concentration is only and only property of the surface active molecules, and we have demonstrated that. So I told you that the conductivity and surface tension are the most conventional or the convenient ways to evaluate that if a molecule is surface active or a surfactant or not, where the micelles can be formed or not. Then we talk about the anatomy of the atom. Anatomy cell, to just understand that if we have to use it for the solubilization process, and how we can solubilize that. The relevance of that that discussion was when you are putting the soap in the washing machine, so you have to have micelles. You have to take a 1 spoon of big spoon of the surf or any soap, and you have to put it in the washing machine. That that has sufficiently much higher concentration than the total volume of the water you are going to take, concentration than the micelles, CMC. So it means that the volume of the water you are taking in the washing machine, and you are putting a 1 teaspoon of the powdered soap, so that will certainly produce a micellar solution. And that micellar solution has ability. It's not always the soap your dirty clothes are having. So it is the what we say those uh, ਉਹ ਜੋ ਸਮੋਸਿਆਂ ਤੇ ਪਾ ਕੇ ਖਾਂਦੇ ਮੈਂ ਭੁੱਲ ਗਿਆ ਕੀ ਕਹਿੰਦੇ ਆ ketchup and all those stuff, so that is water soluble. So those are containing polar components, oil containing the non-polar components. So everything is solubilized because micelles are there, and you have learned that the mice can solubilize everything. So that is the reason when in your washing machines micelles are there, no matter the dirt which is or the dirty clothes, those are being created by the polar or the non-polar dirt particle. They are all going to be solubilized by the micelle. Then we shift to slowly the thermodynamic properties. If you want to have the quantum information, stability of the micelle, we talk about that. In order to have the stable micelles are required. I told you to have the proper bilayer around a nanoparticle, right? And the stable micelles will produce stable colloidal solution that we will talk about in next lectures. So stable micelles, quantitatively, how can we calculate? We can calculate when we have the stronger hydrophobic contribution of the free energy that will help us to create the stable micelle formation. Eventually, we have gone to slowly to the cleaning process, mechanism of the cleaning process, and that of the biological application. And this is the first biological application that will help us to understand the bioapplicability of our nanoparticle. And you see, today we have completed 4 lectures, but we have not yet arrived at the iron oxide nanoparticle. I do not want to take you directly to the iron oxide nanoparticle. The reason is that you are more familiar with the gold or the silver nanoparticle. So therefore, first you need to understand the behavior of those nanoparticle. If you are clear about the behavior of those nanoparticle, and then you will not be having any much problem in understanding the behavior of iron oxide nanoparticle. And eventually, so I'll be taking you to iron oxide nanoparticle, synthesis, stabilization, and then their bioapplicability. Thank you so much for your attention. Any question, please?
Parameters for the bilayer monomer or micelles.
Yeah, so bilayer is in fact, you are saying that the bilayer, the thread-like micelle, rod-like micelle, which you were, yes, absolutely, you are correct. Actually, the thing is that whatsoever the treatment you are applying to, the aggregated state, micelle, spherical micelle is the first aggregated state that is being produced from the monomer to that of the micellar state. But the rod shape or the bilayer is the transformation of the micelle. No aggregation is means the kind of aggregation you have expected from the monomer to the micellar state. That kind of aggregation is not occurring. It is simply the structure transformation of the sphere to rod, rod to ribbon, ribbon to vesicle. And so therefore it's a structure transmission. But the actual thermodynamic treatment which we have talked about over here, that is applicable to the micelle, right? So first we will apply to the micelle, and then we talk about the stability of the micelle further when it's going to undergo the shape transformation from the sphere to rod or thread. Okay, thank you so much. See you next time.